welcome to episode 4 of the KZ440 EV Restomod. So this one's been a long time coming, and it's a massive installment that follows the entirety of the 12-volt system. So everything from custom wiring through the installation of the mo.unit, the Motoscope Pro digital dash, as well as the integration of the DC-DC converter, which is used to convert the traction pack voltage, so anywhere between 100 volts when it's fully charged all the way down to about 70 volts, to a constant 13.8 volts to drive all of the 12-volt systems. I'll also be cutting the tank in half and modifying it so there's somewhere to put the 12-volt kit. This is the original ABS and speedo sensor ring that was used on the KTM wheel, but since I'm using the Kawasaki wheel on the front end, the ring won't bolt up to the hub, because just like the issue I had with the brake disc, the PCD is completely different. The diameter would also put the sensing section right where the brake disc bolts up to the hub, so this would need a pretty significant redesign, along with a bracket to move the sensor location. So rather than go down this path, I think there's a better solution. And what I want to try instead is to use the Motoscope Pro digital dash for it. And so I've done a real quick and dirty wiring job because I want to test out the idea and see if I can actually get a pulse out of the motor controller that will drive the speedo on this thing. So the Motoscope can actually be calibrated to a wide range of different pulses. So I'm hoping that whatever comes out of that motor controller is going to be usable for a speedo signal. So let's give it a go. Oh, that's a bit fancy. Yeah, let's give this a try. So that's a great sign. I think this will calibrate okay for a usable speed signal. The Motoscope manual shows the process for calibrating the dash to a speed signal input. The calibration process needs to be done at a constant speed of 50 km an hour in learning mode. Because the build is sitting on a bench, I should be able to get the calibration done by working out how fast the wheel needs to spin and then monitor the speed in the motor controller software. This means I can run the calibration with the bike actually stationary. To work out how fast the wheel needs to spin for a 50 km an hour travel speed, I started by finding the circumference of a 130/80 R17 tyre, which is about 2009 millimeters. Working this through, I would need to maintain a wheel speed of roughly 414.8 RPM. After watching a marker spin on the wheel, as far as I could tell, 1 rotation per second, or 60 RPM, gives a controller speed reading of 120. If we work this through, it means I need to aim for a speed value of 828 for 50 km an hour. So it looks like the calibration worked, but on a side note, the dash does require an always-on power source to maintain the programming. Now that the speedometer has been proofed out with the Motoscope, we can look at the DC-DC converter. I'll be using a Vicor 400-watt switch mode unit, which was chosen because of its small size and high output. This model specifically can provide almost 30 amps at 15 volts. The output voltage is also trimmable using a resistor, which means I can set it to 13.8 volts. According to Vicor, the unit needs several filter and bypass capacitors to operate safely, so I've decided to mount these parts around the converter, then use RTV silicon to glue everything down. I've seen this successfully used in an airframe, so it should work on a motorbike. The white paper for the Vicor evaluation board has a schematic of what's needed at a minimum to run one of these converters. I've just taken the capacitor values from this. Vicor has an online tool that can help with sizing the trim resistor. At this point, I was aiming for a 13.8 volt output, which needed an 11.5 kilo ohm trim down resistor to be added between the SC and the negative sense pins. The output's been wired into a H4 globe. If this turns on, then everything should in theory be working. Okay, so far so good. Showing 96.4 volts on the main pack. Sure enough, 96.4 across the inputs. Then the trim resistor should have pulled the output down to 13.8 volts. And we're seeing 13.79, so that's pretty much where it needs to be. Here's the DC-DC converter mounted to the heatsink. These tabs here, they're basically just there to hold the glands that keep the cables secure. So the whole thing's now been bolted down. Should be able to deal with the vibrations pretty well. The heatsink is quite oversized as well, so there shouldn't be any heat issues. So I want to try and modify the original tank and use it to house and mount all of the 12 volt equipment. The great thing about the tank is it's basically a waterproof case or a housing, and there's enough room on both sides so that I can mount a small 12 volt battery, a DC-DC converter, the charge controller, as well as the mo.unit. So that means that all of the 12 volt components can stay completely isolated from the high voltage section. So here's the concept for cutting the tank in half. I'm thinking cutting around the outside of where the tape line is. That will then give a little bit of a lip on the top of the tank. So if I then weld a lip around the bottom to sit inside here, then I can bolt those two sections together. And with some weather stripping around the outside, it should create a waterproof seal. The idea behind cutting the tank where I did was so that once everything was mounted and wired in on the bottom half, the top of the tank could slip into the front mounts and then pivot down onto the lower half and bolt together. This means I'll be able to access what's inside without having to unplug a stack of wires from underneath. I'd never welded anything as thin as this tank before, so I found a few good sheet metal tutorial videos before starting to tack everything together. It wasn't too difficult, and eventually I got all the way around by keeping the heat to a minimum. The tank was made from a really thin gauge steel that I measured at a bit over 0.7 millimeters. The new lip that I'm welding around the base is 1.6mm hot rolled sheet stock, so that some amount of rigidity can be added back to the tank since it'll be in two halves. I decided to cut out and patch some of the contours to make the space a bit wider so the battery would actually fit inside the tank. The masking tape was used to make a template, which was then stuck onto a piece of sheet to cut a patch. And this is where I switched welders. The MIG welder I was using earlier is a transformer unit, so I only had really coarse adjustment, and I found it really hard to get a setting that worked consistently on sheet this thin. I just couldn't get it to butt weld the original tank without constantly blowing through the edges, so I decided to try my luck with a new TIG welder. And after some tutorial videos, an online course, and a few hours of practicing on coupons, I moved back to the tank to finish off the changes. And here's the majority of the changes done, with all the mounts and brackets added to hold everything in place. Now after some cleanup with a flat disc and some evaporust, it's ready for a test fit. I decided to use the Motogadget Mo.unit as the body controller for this build. This is a Bluetooth-enabled power distribution module that simplifies wiring with digital fusing and solid-state switching. This significantly cuts down wiring complexity since it completely replaces the fuse box and all relays. So looking at the inside of the tank, there's a fair bit of space just here where I can actually bring the wiring loom in and have a lot of clearance in and around the inside of the tank. So I'm probably going to use either a grommet or a gland of some sort, probably around here. And then given that there's a huge amount of space between the frame and the tank, there shouldn't be any clearance issues at all with the wiring. So now that all the 12-volt bits are located in the tank, I can rough in the wiring loom back to the Mo.unit and the battery. I started this process by adding zip ties along the frame and at the terminations so the wires could be laid out roughly where they'll run. This allows the lengths and routes to be worked out relatively easily. Once everything is laid out and connected back to the Mo.unit, I can partially bind up the loom until the terminations for the lights and other bits are properly located, so I know where to put the plugs along the final run lengths. At this point, I'll be able to then heat shrink it all up properly. The new wiring loom is now roughed in, with most of the 12-volt runs in place for the handlebar buttons and switches, the lights and blinkers on the front and rear of the bike, as well as the tail light, the kickstand switch, brake switches, and the horn. The charging and BMS looms still need to be added here, but I'll probably run them separately to minimize the chance of interference along the ISO SPI and the CAN bus links. I wired in the Mo.unit to test all the functions and make sure I've not overlooked anything with the wiring runs. All the basic stuff worked first time out of the box with the default settings, and running a few spare wires around paid off for some unforeseen changes. I ended up paying a bit more to get the Bluetooth version, and I think it was totally worth it because once I paired the mobile app, all of the settings could be configured remotely with the UI. The mobile app also doubles as a dash screen when it's rotated horizontally. Using an IMU from a paired phone or the Motoscope dash, the app can show a range of data from system voltages and positioning to 0 to 100 times, tilt angles and deforces. So I've made a bit of an incorrect assumption when it comes to wiring in the Mo.unit and the Motoscope dash. I've actually plugged the two together using the LIN bus. What I was hoping for is that it would act similar to a CAN bus and be able to drive things like the dash lights from the Mo.unit. Now that unfortunately will not work. That's not the way that it's been designed. And Motogadget actually have this breakout box to do exactly that. So this connects to the dash using a LIN bus, and basically it takes a tap from all of your lights, either from the Mo.unit or from the loom directly. This then encodes that information and sends it up to the dash via the LIN bus. Now, in doing a little bit of reading, I think that the reason for this is that LIN bus is actually a master-slave protocol. which means that you need one master device to control the communications between all of the nodes on a bus. Now, because Motogadget has actually released the mo.unit and the Motoscope Dash as two separate standalone products, they each have a series of supplementary devices that you can plug in via the LIN bus that's specific to those products only. There's no interdependence between the mo.unit and the Dash, so it's difficult to then nominate a master to control all the communications across both products. So I've more or less finished the bench test wiring for all the 12-volt systems, and you can see that I've got the breakout box off to the side here. It's all wired into the mo.unit. You've got the taps here for the left and right blinker, as well as the high beam, and then the auxiliary out is where the power comes from. So as soon as the mo.unit gets turned on, it actually enables the breakout box and starts sending all the information across to the Dash. The other two things I've got down the bottom here, being the breakout box version B, this one actually has inputs for things like the coolant temp sensor, oil temps, air temps, and things like that. So I've actually repurposed the coolant temp and the air temp sensors to monitor the battery temperatures. And with the coolant temp sensor specifically, I'll set up an alarm so that when the battery temperature reaches 55 degrees, I'll actually get an alert on the Dash. So that's to help manage the heat within the battery pack. Now, I didn't want to use an actual coolant or an oil temp sensor for this because they're quite big and have a fairly significant thermal mass. These sensors would take way too long to register a change in the battery temperature, so I wanted to find an equivalent in a thermistor. I managed to track down the VDO sensor that's used by Motoscope for the coolant and oil temps. The spec for this sensor is 50 to 150 degrees C with 322 ohms at the 50 degree measure. A 1 kilo ohm NTC thermistor measures around 349 ohms at 50 degrees, which is very close and should give an acceptable reading. Once the sensors were hooked up, I used some hot water to test out the accuracy. I had a standalone digital thermometer and also a thermocouple for my multimeter, so I used those as a benchmark to see how close the Motogadget Dash could get. So the Dash showed 61 degrees, while the thermometers were in the low to mid 60s. This is close enough, and using a 50 degree set point for the overheat alert should provide enough tolerance for a few degrees of deviation. The Dash lights are working exactly as they should, so the breakout box appears to be wired in and functioning correctly. The design for switching between the DC converter and the backup battery has also gone through a few changes and now uses a pair of low loss diodes instead of a relay. The system should always prioritize and run off the Vicor converter unless there's a primary pack failure, where the battery can power lights for up to about an hour. The inline resistor is there to limit charge current into the battery, which should gradually reduce to zero as the converter and the battery voltages converge during charging. This is not an ideal charge profile for a lithium pack, but it's literally just for backup and also maintaining programming for configs in the mo.unit and the Motoscope. I've added a temporary tap to the DC converter output to compare the actual current draw to what the Mo app is showing. If these are similar, then the DC converter should be the priority source for power over the backup battery, which is exactly what we want. It looks like the current draw is slightly higher on the multimeter than the Mo app total, which is to be expected because there'll be a small amount of current getting pulled through the charge resistor that won't be registering in the app. So it looks like the diode solution is working as it should and prioritizing power from the DC converter when it's operating, then allowing the power to flow from the battery once the converter is off. This should satisfy the backup requirements in VSB14. I've used XT90 connectors from the DC converter output, and while this plug is a bit over-spec'd, the terminals were large enough to solder the 3 discrete outputs I needed, one for the mo.unit and the battery, another for the motor controller, and a third for the high current output for accessories. That's it for this installment, but on the next episode we'll be diving back into CAD to design the traction pack housing, do the FVA analysis on it to make sure that it's going to be road legal, as well as starting to pull everything back into the frame and bring everything together. If you like this episode, please don't forget to like and subscribe so you can get updates for the next one. And before I finish, I'd like to give a huge shout out to some talented engineer friends, Rob, Scott and Paul, for your input and steer during this episode. Massive kudos.